Hey everyone, it's Jay. Today's video is on the action potential in a neuron. Before we get started, you're going to need to be familiar with the resting membrane potential in a neuron and why ions move the way they do. It'll be helpful to have watched the video on graded membrane potentials that you can find linked on the master list. The function of the nervous system is communication. A neuron will monitor what's going on in one location and then send a signal to target cells to tell them what's going on so that they can behave appropriately. The signal sent down the axon is an electrical impulse called an action potential. The resting membrane voltage at the axon hillock is about a negative 70 millivolts. In the membrane in this area, we see voltage-gated sodium channels and voltage-gated potassium channels. Voltage-gated sodium channels open when voltage inside the cell rises above a negative 55 millivolts. We call this the threshold voltage because once the membrane potential rises above negative 55 millivolts, the voltage-gated sodium channels open, and that's what causes an action potential. Let's look a little more closely at how that happens. Graded membrane potentials are always affecting voltage at the axon hillock by changing the way ions move across the cell membrane in the dendrites. When enough positive charge enters the neuron that voltage at the axon hillock rises above threshold, this voltage-gated sodium channel is going to open. When that voltage-gated sodium channel opens, sodium rushes into the neuron, and the positive charge opens the neighboring voltage-gated sodium channels. So this is a positive feedback loop where sodium entering through one open voltage-gated sodium channel causes entry of more sodium at the neighboring channels, which in turn causes the entry of more sodium. There's a wave of depolarization that travels down the axon as open voltage-gated sodium channels cause all their neighbors to open. Voltage along the axon rises quickly to above plus 30 millivolts. This causes voltage-gated potassium channels to open, and the voltage-gated sodium channels flip into a third shape we call inactivated. An inactivated voltage-gated sodium channel doesn't let sodium into the neuron, but also doesn't open even though the cell is depolarized. So at this point, sodium can't get into the cell, potassium is leaving the cell. This causes voltage inside the neuron to get more negative. The potassium channels actually stay open a little longer than you might think, so the cell overshoots the resting membrane potential and hyperpolarizes briefly. As the cell is repolarizing, the voltage-gated sodium channels flip back into their closed shape. Eventually, the voltage-gated potassium channels close, and the cell returns to its resting membrane potential as the sodium-potassium exchanger is doing its thing. So let's take a look at what's happening graphically. We'll start at resting membrane potential, negative 70 millivolts. As voltage-gated sodium channels open, there's a rapid depolarization. At this peak, voltage-gated sodium channels inactivate, and voltage-gated potassium channels open. This causes a rapid repolarization. As the cell gets more negative, the voltage-gated sodium channels flip into a closed shape. The voltage-gated potassium channels are still open, causing a hyperpolarization. Eventually, the voltage-gated potassium channels close, and the cell returns to its resting potential, with the sodium-potassium exchanger pumping ions to the appropriate place. There are two properties of action potentials that are different from graded potentials. Recall that graded membrane potentials could be different sizes, and they could be depolarizing or hyperpolarizing. Action potentials are all the same size and are only depolarizing. Graded membrane potentials could be different sizes, because a larger stimulus would cause a greater flow of ions across the plasma membrane and a greater change in voltage. With an action potential, Since opening some voltage-gated sodium channels causes them all to open, it's an all or none response. Either all of the voltage-gated sodium channels open or none of them. Action potentials are only depolarizing because they're caused by opening voltage-gated sodium channels. Sodium moving into the cell is always depolarizing. So if we look at a graph of a lot of graded potentials in a neuron, this can be all over the place. But if we look at a series of action potentials, you can see that every action potential is the same size and the same duration. Action potentials happen at different frequencies, but every action potential looks the same. Okay, quick summary. Neurons transmit signals along axons as electrical impulses called action potentials. An action potential is a wave of depolarization caused by opening of voltage-gated sodium channels. After rapid depolarization, the cell repolarizes as voltage-gated sodium channels inactivate and voltage-gated potassium channels open. As the cell repolarizes and then hyperpolarizes, the voltage-gated channels reassume their closed shape, and the neuron returns to its resting membrane potential as the sodium-potassium exchanger pumps ions back to their resting location. All action potentials are depolarizing, and all action potentials are the same size.